So I show some ground design based on optical circuits and waveguide for integrated optical modules, in particular for the Mach sender interferometers. I will briefly introduce why the Mach sender interferometer is key to the high-speed optical modulation, and the physics and the modeling of high-speed phase shifters, in particular on the silicon photonics platforms. And I showed some characteristics of the integrated optical modulators based on silicon photonics design and fabrications. And some integration with the lasers based on silicon-based optical modulator platforms. And if I have some time, I show some emerging technology for heterogeneous integration using lithium niobate as an electro-optic medium. So transmission capacity is actually increasing year by year like this. So if you measure the traffic per month in exabyte, actually it's going up in here in 2020, actually almost 200 exabytes per month. So to meet with this high capacity transmission, actually the key is the enhancement of the modulation speed, and the high speed modulator is actually one of the key elements for high transmission capacity in optical communications. So actually there are several integration platforms. So if you classify these photonic integration technologies along the distance in transmission for optical communications, actually there are two schemes on modulation or signal transmission. One is intensity modulation, optical power is on and off for data transmission. The other one is a phase, using the phase characteristics of the light waves in optical transmission. So phase modulation is the other scheme for the optical signal transmission. Actually, in a longer distance, phase modulation is preferred because of the high quality of the transmission. Intensity modulation is more simpler, and actually in a shorter reach, in particular the on-board or data center applications, actually intensity modulation is preferred with a parallel lane transmission. Actually, in a longer reach, actually single lane in optical fiber is preferred because of the limited availability of the optical fibers in a longer distance, such as 1,000 or 10,000 kilometers and more. So in a shorter reach, actually the key metric is footprint and cost. So in this reach, actually the silicon photonics platform is preferred. And if you go beyond this reach, actually the 3.5 technology is also preferred because of more mature and more suitable to the high-speed communications. And in a longer reach, actually the metric is optical loss for modulation speed because of to maintain the high-quality signal transmission in a longer distance like this. Actually, in the longest reach, still the lithium niobate is the most important material for high-quality optical modulation. But in this region, actually 3.5 and the silicon photonics platforms are also used for optical signal transmission. So in this presentation, I will put more emphasis on these sort of silicon-based platforms and some other material like lithium niobate for heterogeneous integration technology as an emerging technology in high capacity optical transmission in optical fibers. So this is one of the example of the integrated optical transceivers, including optical modulators, parallel line optical modulators as a key element. So actually the footprint on this integrated photonic transceiver is about 15 by 15 square millimeters. So in this footprint, all of the functions, including electronics and optics, are integrated. So in this picture, you see the electronic ICs for signal transmission and signal receive. So all electronic ICs are also integrated by the flip chip bonding, in this case, on silicon photonic chips. And here you see the optical modulators in lanes from channel 1 to channel 4. So these integrated parallel modulators will work as a key element for high-speed optical transmissions. So in this circuit, parallel, so 4 lanes of the Mach-Zehnder interferometer modulators are used. So this chip can be mounted on a PCB to assemble QSFP, active optical cable, or other optical transceivers in a small footprint and low profile. So these parallel lane devices have an advantage of increasing packing density in a small form factor optical transceivers. Also, some other technologies are required, like integration in a lens in optical fibers. For example, a multi-core fiber. In this case, 4-core fiber is utilized to transmit parallel lane optical signals in a fiber. So the other example in a single lane application in a longer reach is polarization division multiplexed quadrature phase IQ modulators. So that this is the IQ modulators integrated on a silicon chip with a monitor germanium photodiode. And you see that these fibers are actually mounted on a chip. So in this chip, you see that this actually the length is 3 millimeter. Actually, the phase shifter in the Mach-Zehnder interferometer has a length of 3 millimeters. Actually, so the each phase component and the X and Y polarizations are integrated on chip with a polarization division multiplication waveguide. I will briefly introduce this sort of the waveguide in a later slide. So if you deal with optical modulators, actually there are several types. The most simplest one is the intensity modulator using electro-absorption modulators on, for example, on a silicon photonics platform or a 3.5 photonics platform. So this is very simple, just straight waveguide with electro-absorption waveguide. So if we apply electrical signals, you can change the absorption coefficient of the waveguide quite electrically, electrical signals, and you can on and off the optical signals. The other one in intensity modulation is the ring modulators. So the straight waveguide is connected with the waveguide ring, micro rings, to modulate the optical signals by a ring resonance. So that this ring modulator has the advantage of the low voltage modulation in intensity modulation schemes. And the bottom one is the Mach-Zehnder modulator, MGI modulator. Now I'm dealing with. So we have this sort of interferometer arms in a waveguide systems with a 1x2 splitter and a combiner. So this form interferometers, and this type of the modulator based on the Mach-Zehnder interferometer is used both for intensity modulation and phase modulation. For the both type of the modulation is realized with this one modulator. So this is most useful in optical modulation in optical fiber communication systems. So the why the people in the community utilizes the Mach-Zehnder interferometer so heavily is due to the with this just one modulator, you can do the intensity modulation and phase modulation. So this is the basic mathematical representation of the Mach-Zehnder interferometer. So in one arm and the other one, electrical data and inverted electrical data is applied in these schemes. Actually, we call the push-pull modulation. So the positive and negative signals applied in each respective arms, vice versa. So in one arm, the electrical signals, electric field of the optical signals is represented in this scheme, and the other one is just phase is inverted. So if you combine these two optical signals with a 1/2 optical coupler, you have output electric field like this. Just you can represent output electric field in a real part only. So this is why this scheme is actually push-pull modulation. You can generate a real part of the electric field only. And this is actually the key to generate high quality optical signals free from frequency distortion. We call the frequency chirping. So to avoid the frequency chirping, this particular real part of the electric field generation scheme is important for high quality transmission. And this is an illustration of the Mach-Zehnder interferometer and the push-pull modulation on a silicon photonics platform. So you see the interferometer waveguide, and in each arm there is a phase shifter, and phase shifters, the cross section is like this. So you see the RIP waveguide and with dimension like this. So a very tiny nanometer scale waveguide with RIP wings to apply the electric voltage, signal voltage for the modulation on each wings of the RIP waveguide. So that these slab parts on the both wings are utilized for the electrode to apply the high-speed electrical signals to the phase shifters. And in a silicon photonics platform, actually the PN junction is formed to generate the carriers, electrons and holes in a waveguide and to modulate the density of the electron and holes to generate refractive index modulation for optical modulation in these phase shifter arms. So basically the Mach-Zehnder interferometer modulator generating a phase shifting, so phase modulation. And if you combine this with a 1/2 couplers, you can generate intensity modulation or phase modulation as well. So this modulator is actually this modulator is designed to realize a high contrast modulation based on optical interference. So the on and off with high contrast and high quality phase modulation is possible. And for high speed modulation, PN junction is applied with a reverse bias to avoid the slow movement of the carrier diffusion in a forward bias carrier injection. So the reverse bias, actually the carrier drift is limiting the speed of the modulation apart from the RC time constant. That's also the factor to limit the modulation speed. So the RIP waveguide with the PN junction is the phase shifters, and two arms of the phase shifters are connected with a channel waveguide to have interferometer waveguide for optical modulation. And these waveguides are formed on a silicon wafer, like this cross-section schemes. Actually, you see that this wafer, this is actually the 200 millimeter diameter wafer, and there are several dies on a wafers, and each dice contains passive and active elements for the optical modulators and for the other optical circuits. So the wafer is a SOI wafer is utilized, a silicon non-insulator wafer, and optical waveguides are formed on this top thin silicon layers as thin as 200 or 300 nanometers. So this sort of the passive waveguides are formed in this top thin silicon layers, and also the active element. For example, phase shifters with a PN junction, and also photo detectors, photodiodes, using germanium crystals for active element. So this is the integration scheme on a wafer. So the wafer level integration for passive and active elements for the optical modulators and other elements in optical transceivers. And the other one is other integration scheme is on package or in package integration or co-packaging with a photonic circuit like integrated optical modulators with electrical modulators. For example, modulator drivers and other electrical circuits. So all of the elements in a photonic and electronic functions are co-packaged in a small footprint, low profile modules like this. So this is the integrated optical modulators to packaging with a photonic and electronic elements. So on chip or on wafer integration and also on package integration, both aspects are very important for realizing a small footprint, high-speed optical modulators for signal modulation. So to design the optical modulators, there are some keys to deal with this sort of the optical modulators, including Mach-Zehnder interferometer circuit. So the mathematically the two-port scheme is actually the advantageous. So we actually modify the single-port Mach-Zehnder interferometer circuit into this two-port interferometer schemes without loss of the generality. So in the real modulators, actually one input and one output, and the input signal is modulated. So if you consider the intensity modulation, actually the interference is actually the constructive. Actually, the high intensity of the optical signal is output. But if you have a destructive interference, actually no output from the output port. So in that case, the optical energy is lost out of the waveguide by a radiation mode. So if you convert this single port conventional Mach-Zehnder interferometer scheme into a two-port scheme, so you can assign one of the port as the output port, and the other port is actually the radiation mode, port for the radiation mode. So actually one of these two output ports is used for the optical signal transmission, and the other one is unused. And this port can be regarded as a radiation mode in for the case of the single port, single output and input port Mach-Zehnder interferometers. So why this two-port scheme is actually important is represented in this slide. Actually, if you utilize the two-port schemes, you can use this sort of a very simple scheme of the transfer matrix method to deal with the Mach-Zehnder interferometer mathematically. So you can use 2x2 matrix to construct the Mach-Zehnder interferometer or even other more complicated scheme for the IQ modulator or polarization multiplex modulator. So in this case, just a single Mach-Zehnder interferometers. So if you assume a two-port interferometers, so the input signal E out and output radiation mode E rat is actually represented in this simple signal scheme. And you can deal with the Mach-Zehnder interferometer by this sort of a transfer matrix. This is very advantageous to construct more complex optical circuit with high port counts based on this 2x2 schemes. So that's actually the very rough sketch of the interferometer circuit. And the next step is to deal with the optical mode in each type of the waveguide. So some numerical modeling or simulation is required to analyze the light propagation in this type of the waveguide. So this equation is the basic equation to analyze the light propagation in the waveguide. Actually, this is a wave equation, and the most important thing I have to emphasize is this term, the second term on the left hand of this equation. Actually, usually if you assume low index contrast waveguides such as the silica optical fibers, actually this term is neglected. The conventional wave equation just contains this the first term and the third terms only. But the high index contrast waveguides such as silicon waveguide or 3.5 based waveguide, actually this part is not negligible. So you have to solve this full form of the equation in a vector wave schemes by numerical simulation. So actually, I have utilized the two types of the method for the analysis. One is the FEM, finite element method, and the other one is the field model matching method. Actually, both methods can generate the similar signals. So anyway, so you can utilize this sort of the method for your design. So you can generate the mode field like this by the numerical simulation. So other element such as 1x2 splitter is also analyzed based on that kind of numerical schemes like this. So you can do the numerical modeling with the wave equation in a vector mode schemes for design the optical modulators. So you can analyze the other waveguides such as polarization division multiplexer like this to convert optical polarization in TE to TM schemes. Actually, this sort of a waveguide is important to multiplex optical signals in orthogonal polarization components. So these sort of the waveguide are made on silicon photonics platforms. And the other aspect is related with the phase shifters, so the active devices. So to control the optical properties of the waveguide by the electrical signals applied from electrical drivers or signal processors. So in a crystalline silicon, actually the crystal silicon has an inversion symmetry. So no electro-optic effect, Fokker effect is absent in a silicon because of the inversion symmetry. So instead of the Fokker effect, we utilize a free carrier refraction or free carrier dispersion for intensity modulation or phase modulation. That's actually due to the interaction of the light field of the free carriers in a single particle Drude model schemes. That is actually the illustrated in this slide. So the electric field of the optical signal light wave is input to the waveguide with the doped with the carriers. So the electric field is interacting with the carriers. And the energy transfer from optical electric field in the light wave to the carriers, that will cause absorption, free carrier absorption, and free carrier refraction as a counterpart of the free carrier absorption. And this is the key to generate the phase modulation or refractive index modulation to generate the phase modulation by the electrically. So that this is the mechanism for optical modulation in silicon, crystalline silicon for silicon-based optical modulators. So in a detailed analysis is actually based on the Drude equation for single particle charged carriers. So you can do the analyze the interaction of the light field with the carriers based on this Drude model. And actually the characterize the change in absorption coefficient and the change in the refractive index as a function of carrier densities based on data schemes. Actually, the dotted dashed lines in this graph are based on the Drude model equation. And the solid lines is some empirical formula by refractive index or absorption coefficient measurement in a doped silicon crystals. But basically, that you can reproduce these measured characteristics by the Drude models, but there are some discrepancies. So to design your optical modulators precisely, so basically this empirical formula extensively used. That's actually based on the group by the Sorev. And if you want to look at the more details of the empirical formula, you can check this reference. And actually, we are dealing with actually the dielectric waveguide, not a metallic waveguide. So actually, there are some limitation of the doping concentration to avoid the metallic interaction. So actually, the doping concentration up to 10 to 19 per cubic centimeters. Actually, that in this range, actually the plasma frequency is actually getting closer to the optical frequencies. So actually, the waveguide is not dielectric. So you have to be careful to check the dopant concentration to deal with your modulators with the dielectric waveguide. That's one of the limitations in the design. And actually, the modeling of the phase modulation in a PN junction phase shifter in a silicon waveguide can be dealt with this equation. So equation of the continuity and the current flows in a PN junction waveguide. And you can map out the carrier distributions in the waveguide, and you can calculate the phase shift with using optical mode obtained from the finite element method or field mode matching method. And you can generate the phase shift as a function of reverse bias voltages in a simulation and compare that with the measurement. Actually, this scheme of the modeling is very accurate as far as the DC bias situation. So you can design your waveguide, silicon-based waveguide for the optical modulators using these sort of the schemes. And actually the commercial EDA tools are actually using that sort of the schemes. So light field simulation and also carrier distribution by physical simulation are combined with this sort of a transfer matrix format to design the modulators. Actually, these schemes are equipped in a commercialized EDA tools. So in the characteristics, first of all, I show some optical loss characteristics because optical loss is very crucial to very important metric to characterize the optical devices based on the silicon platform. Actually, the sum of the simple waveguide optical loss measurement give these sort of loss characteristics. This is actually the basic information to estimate the insertion loss of your optical modules based on a silicon waveguide. And also 1x2 coupler splitter, multi-mode interferometer is actually utilized for the 1x2 coupler and splitters. Actually, the based on the silicon platform, you can create a very low loss coupler and splitters. Actually, on chip loss is about 0.2 to 0.4 dBs over this wavelength range of C and L bands. So low loss coupler and splitter, and also a low loss polarization division multiplexer. Actually, the polarization conversion loss is only 0.3 dB over this wavelength range, and polarization extinction ratio, polarization source separation is higher than the 20 dB with this PDM waveguide. This is the top view of the waveguide on a silicon photonics chip. And based on this basic element, you can manufacture the optical modulator modules like this. So here is a small footprint integrated optical transceivers, including Mach-Zehnder interferometers in a quadrature phase component and polarization division multiplexers on chip. And you can produce the high capacity optical signals beyond 100 gigabit per second per lambda, and signal transmission beyond 2,000 kilometers. So high capacity optical transmission is possible with the silicon-based optical modulators. And one of the other scheme is the integration of other components like 3-5 lasers with silicon optical modulators. So one of the key technology we are using is die bonding for integration heterogeneously with 3-5 lasers. So die bonding 3-5 dies on SOI. And this die bonding scheme is used for integration of the other devices like magnet-optic layers to generate a magnet-optical devices such as the magnet-optic memories or magnet-optic isolators. And also die bonding is also used for integration of the electro-optic layers such as lithium niobate on SOI. So this equipment actually gives you integrated photonic chips by die bonding. So laser integration, 3-5 laser diode on a silicon chip by die bonding is actually is shown is in this view graph as an example. So in this case, 3-5, some type of very thin 3-5 lasers by lateral carrier injection scheme are integrated on silicon chip by die bonding. Actually, this case is the bonding medium is the polymer VCB medium is utilized to the bond the both silicon and 3-5 lasers. And this figure showing the scheme of the integration in the process steps. So in this case, gallium indium arsenide type of the laser dyes are integrated on silicon wafers for high degree of the integration of the 3-5 lasers with a silicon photonic modulator for on-chip optical transceivers. If you want to get more details on these topics, you can refer to this book for further learning. So in the rest of the time, I briefly show the emerging technology, in particular on the conventional, very traditional electro-optic material, lithium niobate on silicon photonic waveguide. So the topic is the slot mode type of the waveguide utilizing a heterogeneous structure, including lithium niobate and silicon. So if we look at this cross-section, you see the lithium niobate in the middle of the waveguide core, and the thin lithium niobate, actually in this case, 300 nanometer thickness. Width is something like 200 nanometers, sorry, 500 nanometers in width and 300 nanometers in height. And this thin rectangular lithium niobate medium is sandwiched between the thin silicon layers with 100 nanometer in thickness. So if you input the vertically polarized, vertical linearly polarized light into the lithium niobate materials, you have a very strong light confinement in this middle of the lithium niobate layers as a slot mode. Even if the index contrast of the silicon is higher, index of the silicon is higher than lithium niobate. But in this case, because of the Gauss laws, actually the high intensity of the light field is confined in this middle lithium niobate layer with a lower index than silicon, the slot mode. So high intensity is confined in the middle of the lithium niobate, and high efficient optical field modulation is possible by utilizing this slot mode in a vertically polarization compared with a rectangular single lithium niobate waveguide. Actually, high intensity electric field is confined in this lithium niobate layers, and high modal field confinement compared in this lithium niobate silicon slot mode compared with the rectangular single lithium niobate waveguide. So low voltage or high efficiency in the optical modulation, more than twice compared with the conventional lithium niobate waveguide is possible with this sort of heterogeneous waveguide. So this is one of the schemes for high efficient optical modulators on a heterogeneous integration platform with low optical loss. actually the index contrast of the retinal nerve is lower, but optical absorption or optical loss in the retinal nerve is much lower than the silicon. So based on these heterogeneous platforms, utilizing the small footprint of the silicon platform, we can generate small footprint electro-optic modulators for low loss and high efficient optical modulators. So okay, that's actually I presented some of the brief outline of the optical modulators on photonic integration platforms. So now for time for Q&A. Okay, thank you.
Hello. Hello. Am I audible? Thank you very much, sir, for this informative and knowledgeable lecture. Now we can have a couple of questions.
Okay, I see the one question. Give me some more information about MIG. That means the MGI? So the question is one question is some more details on Mach Zehnder interferometer. Okay, so this is the basic scheme of the interferometer. It's just the waveguide for simple optical interference in a traveling wave forms. So input light is separated into two arms, and each arm has a phase shifters. So optical phase of the light waves in both arms are shifted by the electrical, and actually that they are combined at the end of this interferometer arms into one path. So actually in each path is actually the electric field of the light waves represented like this. And after after combining both fields, you have output electric field like this. So actually this term V is actually the voltage applied externally. So half of the V is applied to this arm, and half of the other voltage applied to this arm. So actually the difference between these two phase difference between these two arms is actually like this. So actually, if you change the voltage, you have some change in optical phase. So there is no difference. For example, zero voltage. Actually, the cosine zero gives you just one, so a constructive interference. But if you have somehow the voltage to generate half pi, 90-degree difference in optical phase, you have this term is actually the zero, so you don't have any output. So by changing the voltage, you have on and off of the electric field. And so this scheme is actually implemented on silicon photonics platforms like this. Okay, so the next question is, PBG and EBG are different. What does the PBG stand for? does it mean the photonic band gap?
Yes, sir. It is photonic band gap, I think.
And the EBG, electronic band gap.
Yes, sir. Electronic band gap.
Actually, yeah, that's different. Actually, the photonic band gap is defined with the array of the dielectric materials. So if you change the pitch of the array of the dielectric medium, you can change the photonic band gap. But there is no change in electrical band gap. Electrical band gap is actually determined by the material crystalline properties of the material. Like if you have a silicon crystal, you have a unique band gap energy for the electron band gap. So that's actually the electrical band gap is determined by the array of the atoms in a crystal. But the photonic band gap is determined by the array of the dielectrics of your lattice arranged in optical designs. So that they are different. And the third question is, yeah, actually the magnitude of the electrical data and inverse electricity, that should be the same. So both of the signals should be the balance to generate the high quality of the optical signals. So if you apply the plus 1 volt in one arm, you have to apply the minus 1 volt to the other arms to get a good balance between the optical signals. So those are my answers to the questions.
Okay. Thank you very much, sir, for accepting our request to deliver a talk. And the talk is really very, very beneficial for all levels, UG, PG, and PhD also. And once again, I thank you from the behalf of OSS Student Chapter MNIT. Also thank all the participants for attending this lecture. So thank you from us.
Okay, thank you for your interest.
Thank you, sir. Thank you very much.
Bye.